looking at the topic of discrete probability distribution, and the first part of that is probability distribution. Probability distribution, basically what we have done, we have looked at describing data, we have looked at probability, and now we're going to combine these two with what we call a probability distribution. So combining descriptive methods and probabilities, construct probability distributions by presenting possible outcomes along with their relative frequencies. In essence, in the case of a discrete random variable, I hope everybody remembers when we looked at quantitative data, we said there are two types, discrete and continuous. And discrete is countable. So in the case of a discrete, we have basically two columns, the outcomes, what X represents, and then the probability for each case. Those two sitting next to each other, they define for us what is called probability distribution for a discrete random variable. For a continuous random variable, there are infinitely many numbers in between, and it becomes a continuous function and a continuous graph. Key concepts: probability histogram is a graph that visually depicts a probability distribution. We want to find its important parameters, which are mean, standard deviation, and variance. We want to determine whether outcomes are significant, that means significantly low or significantly high.
A random variable is a variable typically represented by X that has a single numerical value determined by chance for each outcome of a procedure.
Next paragraph, probability distribution.
Probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. A discrete probability distribution consists of the values a random variable can assume and the corresponding probabilities of the values.
The next one, discrete random variable, and remember we're going to use DRV for short.
A discrete random variable has a collection of values that is finite or countable. If there are infinitely many values, the number of values is countable. If it is possible to count them individually, such as the number of tosses of coin before getting heads.
And finally, continuous random variable. Sometimes we use CRV to represent that. CRV versus DRV.
A continuous random variable has infinitely many values, and the collection of values is not countable. That is, it is impossible to count the individual items because at least some of them are on a continuous scale, such as body temperatures.
So those are some definitions we need to know. So there are three requirements for a probability distribution to work. Number one,
there is a numerical, not categorical, random variable RVX, and its values are associated with corresponding probabilities.
And the next one?
The sum of the probabilities is equal to 1, where X assumes all possible values. The sum of all probabilities must be 1, but some such as 0.999 or 1.001 are acceptable because they result from rounding errors.
Finally, the last one.
The probability must be between 0 and 1 for every individual value of the random variable X. That is, each probability value must be between 0 and 1 inclusive.
So in short, what are the requirements? Got to deal with numbers. The sum is always 1 or 100%. Sometimes, due to round off error, we may have a very close number. That is understandable. Finally, probability can only be between 0 and 1. So that's the main thing we want to get out of this section for now. Probability distribution. In the first example, we are constructing a probability distribution for rolling a single die. Just remember, all you have to do for a DRV, discrete random variable, all you need is X and P of X. All you have to do, fill up those two columns. So X in this case represents the outcome, and P of X the probability of that specific outcome. Now, when we are dealing with rolling a basic die, there are 6 sides, and so X can be number 1, 2, all the way to number 6. Also, the probability for each case is equally likely, it's 1 out of 6. So this is basically what we mean by probability distribution. In this example, we are given the probability distribution. So if somebody says, what is the probability distribution for a sample space or for tossing 3 coins, this is given right here. Now understand, for 3 coins, depends on what X represents. By the way, whether it represents the number of heads or tails, it works out to be the same. I want you to know. But specifically, X represents the number of heads. And since there are 3 coins, then we have only 4 choices, 0 all the way to 3. Now, we have seen the tree diagram for this. We have seen the sample space for this. We have seen the probability for each case previously, so I don't think you have anything to worry about. To remember that the probabilities on the second column are as follows: 1/8, 3/8, 3/8, 1/8. And again, you could always do this. Remember, we did it for genders, so this works out the same way: H and T, H and T, H and T. So the first stage, the second stage, and the third coin, that means the third stage, or 2 cubed, or 8 outcomes. The third one goes something like this. For example, if you put H here, this means H, 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 and this last one means T, T, T. And you can fill up in between. So all we have to do in this case, we want to represent it with a graph or a number line. So all you have to do, just come up with a horizontal line and a vertical line. Horizontal line represents the X. And so the X could be 0, 1, 2, or 3. And the vertical axis is the frequency or percent frequency, which really becomes the probability here. Frequency, or in this case, percent frequency or probability. Needless to say, you realize the left column in both cases are numbers, and the right column, the probability, they add up to 1, and they're all between 0 and 1. Here's the next one. Tossing 2 coins, where X represents the number of heads, and we end up with the following given at the bottom as the probability distribution. So if somebody asks you what is the probability distribution for a specific case, if it's a discrete random variable, it simply means come up with the following table. Of course, if X, we have too many of them, then it may be difficult to set up the whole table. We may even give a formula, just as an example. So with that being the case, there are 2 coins, so we have maximum 2 possibilities for number of heads. And again, you can go with the tree diagram, look at what we have done before. Is this a probability distribution? Well, the first thing we need to look at is the first requirement. There were 3 requirements. In short, the X should represent a number. It should be numerical. Some must be adding up to 1, and none of them is beyond 1. That means larger than 1 or less than 0. The variable is a numerical random variable. So far it works, the first requirement. The second one, the sum must be 1. So we add up the second column, 0.25, 0.5, 0.25, and they must become 1. And as you can see, the second column, all the numbers are between 0 and 1. So therefore, the answer is yes, absolutely. So X is a discrete, and remember, discrete means numerical in essence. So even if you just said it's a discrete random variable, that's good enough. Discrete means it is a discrete numerical value. It's countable. So there are 3 possible values. 3 is a finite number, and it satisfies the requirements of being finite as explained in the 3 steps. So basically, when you do those 3 steps, 1, 2, and 3, that they have a check mark next to them, you're done. Probability distribution, a probability histogram.
Probability histogram is a graph of probability distributions that displays the possible values of a discrete random variable on a horizontal axis and the probabilities of those values on the vertical axis. A vertical bar represents the probability of each value, and its height is equal to the probability. And then this is a probability histogram for a number of heads when 2 coins are tossed.
When we did the histogram, the vertical axis could be frequency or percent frequency. In essence, we are really using percent frequency which is now the probability. That's the idea behind this. So with that being the case, a probability distribution could also be in the form of a formula. For example, if this one is given, a P of x is 1 over 2 times 2 minus x factorial times x factorial. So that's the formula. And for x equals 0, 1, or 2, that means it works for those three numbers. You're going to replace the x with 0, come up with the answer. 1, come up with the answer. 2, come up with the answer. So the idea is sometimes we may have a formula. And normally when we have so many numbers, as we come across it later on in this, you can calculate each one. I'm assuming nobody has any problem calculating this. P of 0 is 0.25, P of 1 is 0.5, P of 2 is 0.25. And in this case, the reason we end up with 2 only because we are dealing with 2 heads max. And it's very easy to calculate. You can try this on your own to make sure you come up with the correct answer. A probability distribution can be represented with a table, as we did it in the previous page. We can represent it with a histogram, with a graph, or with a formula.
Hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution?
So what do you think? Does it?
No.
No. Any idea why?
They're not numerical random values.
If you look at the very first one, is that x is supposed to be a number. It's not. You don't even have to check anymore. I want you to know that. But let's check everything. So the first one is out. So is this as a probability distribution. But here's how it works. Okay, the first requirement is not working. The second requirement is not working. The third one, each one is between 0 and 1 is working, but really 1 is good enough to say this is not describing a probability distribution. Let's look at some formulas. So when we deal with probability distribution, there are some parameters of a probability distribution.
Remember that with a probability distribution, we have a description of the population instead of a sample. The values of the mean, standard deviation, and variance are parameters, not statistics.
The mean, variance, and standard deviation of a discrete probability distribution can be found with the following formulas: mean, expected value, variance, and standard deviation of DRV(x). Mean, the expected value of occurrence per repetition. It represents the average value of the outcome.
So let's look at the formulas. Mu or E of x, the expected value, is the summation of x p of x. In other words, if you recall the probability distribution table, you just multiply the two columns and it becomes the next column, you add them up. Variance is defined as sigma squared equals the summation of x squared p of x minus mu squared, and sigma is the square root of that. Now, what I want to quickly show you, I used to prove a lot of things, and I noticed not a lot of students were following, so I'm going to just give you the proof. You can go over that. A couple of things that I want to mention is that how we go from here to here, how we go, for example, from here underneath to here. You can expand x minus mu squared. So x minus mu squared becomes x squared minus 2 mu x plus mu squared. That p of x, which is being multiplied by it, remains. So you distribute that and you get x squared times p of x minus 2 mu times p of x, 2 mu x times p of x plus mu squared times p of x. And so if you write them as such, this is the same as mu, and this is the summation of p of x must add up to 1. That's how you get to the proof if anybody is interested. Let's look at an example. By the way, remember p of x in essence is 1 over n. So given a probability distribution for rolling a single line, and it's given at the bottom, we want to find the mean, which simply put, we are going to use this formula. And all you have to do, multiply the first column by the second column and add them up. So we're going to use this formula. The definition of this formula is very simple. Multiply all the x's by their corresponding p of x, or multiplying the x's by their corresponding probabilities. 1 times 1 over 6, 2 times 1 over 6, and all the way to the end. The last one is 6 times 1 over 6. And we add them up. It results in 21 over 6, or 7 halves, or 3.5. Let's find the variance and standard deviation. You can use any of those formulas. There are 2 ways to calculate them. So we pick one and we start. For example, sigma squared is x, the summation of x squared times p of x minus mu squared. So what does it mean? I want to make sure everybody can see that if we were looking at the table. X squared, that means if you look at the very first column, if you're looking at this one, squared, 1 squared becomes 1, 2 squared becomes 4, 3 squared is 9, 4 squared, and so on and so forth. You multiply it by p of x, and then you subtract the number that you found in part A squared, which is the mean squared, which is minus mu squared. This is what the formula does for us. So 1 squared times 1 over 6 plus 2 squared times 1 over 6 all the way to the end. We add them up, and then 3.5 squared gets subtracted from it. This is the variance, everybody. So sigma squared is 2.91667. Again, when you want to report that, depending on text you're working with, homework, and you name it, they may ask you for a specific number of decimals, or they may expect a specific number of decimals. So you want to follow that. I just wanted to show you if we carry out more decimals, how it looks like, because it's important not to get to what's known as round-off error. So what is the standard deviation? All you have to do is take a root. So when you take the square root of 2.91667, that gives you the standard deviation. Let's see if we can see what it means. It's extremely important to understand the meaning of this calculation. Okay, so what? And that's the idea that is important when we do all of this calculation. If we were to collect data on rolling a single die many times, in other words, just keep on going. This is a general answer for mu for the population. And that means you have to, if you do it enough number of times, it gets closer and closer to the population parameter. Then you have the expected value, the mean, to be 3.5. In other words, if you add them up and divide by size, with a standard deviation of, let's say, 1.70, and if we do the rounding right here, remember, becomes 1.708. Pay attention to the way we do the rounding, because when you do the rounding, you want to be careful not to make a mistake. I was going to write with 3 decimals, and therefore I look at the 4th one and make a decision on the 3rd one. So that's the idea behind all of these calculations, the mean and standard deviation. So we are exploring this concept by looking at more examples. Here's the next one. We are given some data. As you can see, the probability distribution shows the number of trips of 5 days or more that American adults take per year. 5 days, 4 days, 7 days, whatever the case might be. And we want to find the mean. And again, let's understand, when you set up a table, you can set them up in this manner. There are a couple of rows, or you may set up with x and p of x as 2 columns. It doesn't matter. Now, let's make sure we understand the meaning of this table. This table tells us 6% take no trips of 5 days or more. I'm being lazy, I put 5D plus. That means 5 days or more. According to this table, 70% take 1 trip, that is 5 days or more. 20% take 2 trips of 5 days or more, so on and so forth. So this is the probability distribution, that the number of trips of 5 days or more. So now let's calculate mu, which is summation of x p of x. So that means multiply the top row by the bottom row. So 0 times 0.06, 1 times 0.7, all the way to the end. And so we add them up, and that gives us 1.23. And that is the expected value of number of trips. So what it really means is that according to this data, all American adults take an average of that many trips. that are 5 days or more per year. So probability distribution of DRV, discrete random variable, and what it tells us. Here's the next example.
Recall, the table describes the probability distribution for the number of heads when 2 coins are tossed. A. Find the mean, variance, and standard deviation for the probability distribution described. B. Use these results in the range rule of thumb to determine whether 2 heads is a significantly high number of heads.
We are going to calculate mu, the expected value. When you're given tables, you can extend the table if we make up a new column called x p of x. And why are we interested in that? Because look at the formula for mu at the very bottom. It says mu is the summation of x p of x. In other words, the first column times the second column gives us this column we just made up, x p of x. So 0 times 0.25, 1 times 0.5, 2 times 0.25. And well, since they're all done at the same time, let me explain the next one also. We need to calculate the standard deviation, so we need to calculate the variance first. So if we use one of the formulas for the variances, for example, x minus mu quantity squared times p of x. First, you have to have the next column and the sum of that. When we do that, see what we get. 0 times 0.25 is 0, 1 times 0.5 is 0.5, 2 times 0.25 is 0.5, they add up to 1. So mu ends up being 1, and so the next column, x minus mu, so that means 0 minus 1, you're going to square that, becomes positive, times p of x, in the same column is 0.25, and that gives you 0.25. So you got to come up with this column and then add them up. The very last one that says the sum. So we multiply number 1, number 2, and we get number 3. 1 times 2 is number 3. We add them up, we get number 1. Now we use that to get to the last column. X minus mu, 0 minus 1, squared times p of x, which is 0.25. You do the same thing for the next one, you do the next thing, same thing for the next one, and you have all your answers. You add them up, and you're going to write them as follows. Mu ends up being 1. Sigma squared, we add them up to 0.5, this very last column. Now, sigma is the square root of 0.5, and it's like 0.707 or 0.71. So the calculation for this case, if we use a table, it makes it a lot easier. Let's go to part B. We want to use these results and the range rule of thumb to determine whether 2 heads is a significantly high number of heads. Remember, according to the range rule of thumb, we look at mu plus minus 2 sigma. If anything is beyond, it's unusual. The interpretation is that if we were to collect data on a large number of trials, that means you keep on doing that. With 2 coins tossed in each trial, we expect to get a mean of 1 head and standard deviation of 0.71. It really means that you have to do this many times. In other words, if you do this just 10 times or 20 times, it may not be enough that you get the expected value you want or the standard deviation. Just for the sake of argument, if you do that 10 times, it doesn't mean 5 times heads and 5 times tails. It may be like 7 and 3. When you do it 100 times, maybe 55 and 45. When you do it 1,000 times, then it gets closer and closer. That's the idea behind it. And so mu plus minus 2 sigma, that means 1 plus minus 2 times 0.7. According to the range rule of thumb, the numbers are between negative 0.4 to 2.4. So if we use this result, is this significantly high? The answer is no. Why is that?
It's because if the value is between the negative 0.4 and 2.4, then that means that it's not significant. If it wanted to be significantly high, it would have to be higher than 2.4.
Perfect. Look at the numbers. The upper number is 2.4, and since 2 is less than 2.4, we are in good shape. Let's go to the next example.
Lottery tickets cost $2, and out of 10,000 tickets printed, 1,000 have a price of $5, 100 have a price of $10, and 5 have a price of $1,000, and 1 has the price of $5,000. A. Let X represent the net gain and write the probability distribution for winning the lottery. B. Calculate the expected value and the standard deviation.
When we are given a situation like this, we should be able to come up with what's known as a probability distribution table. So what you need to do is to make up a table of 2 columns. In this case, it says let X represent the net gain, and it's important to know what's the meaning of a net gain. X represents the net gain. So if the lottery costs $2, that means the next net gain for everybody is -2 to begin with. Now, if I win the prize of $5, then my net gain is 5 minus 2. If I win $10, my net gain is 10 minus 2. So it's important to understand the concept of a net gain. The money that was paid for the ticket is gone. When we look at the tickets, you see that we have total of 10,000, so they must add up to 10,000. So 1,000 have a price of 5, 100 have a price of 10. So far we have 1,000 tickets here. Then we have 100, let's do that. Then we have 5 that have a price of 1,000, and only one of them has a price of 5,000. So you add them up, and those are the winners, and you're going to subtract from the total of 10,000, and whatever is left is the rest of us that are playing and we are not winning. 1,000 are going to win $5, 100 are going to win $10, and so on. And look at the very last one, that's N, or the sample size, or 10,000 tickets. And how do we get to 8,894? You got to add 1,000, 100, 5, and 1, and that is the number that has to be subtracted from 10,000. That's 1106. And so with that being the case, what is the net gain? When you win $5, that means you won 5 minus 2. 10 means 10 minus 2, all the way to the last one, which means -2. So pay attention to this next column, especially this -2. So you have to put the number as a net gain. So the net gain for those 8,894 tickets or players is -2. Now the next column is very straightforward. Probability of winning. So how many are going to win $5? 1,000 people. So 1,000 divided by a total number of tickets. The next one, how many are going to win $10? Net gain of 8. 100 divided by 10,000. And so on and so forth. So we wrote the net gain probability distribution. Now the calculation, mu is summation of x p of x. So that means multiply the net gain column by p of x column and add them up. That would be x p of x. And then we can calculate the standard deviations, x times p of x. I want to go with that one here. And then I'm using this formula, x squared times p of x. So x p of x, that means 3 times 0.1. X squared p of x means 3 squared times 0.1. Next one, 8 and 0.01. So x p of x means 8 times 0.01. X squared p of x, as an example, let me just write the second one for you. So this one is 8 times 0.01, whereas here it's 8 squared times 0.01. So with that being the case, we add up this column, we get summation of x p of x, or mu, summation of x p of x, or -0.4. And what we have here is summation of x squared p of x. If you go to the top formula, you have to subtract mu squared from it and take a root to get to the standard deviation. So mu or summation of x p of x is negative 0.4. We use this formula and we take a root. I'm not calculating the variance, although you can, because you have to calculate the variance and then take a root. Either way is fine. So x squared p of x, we know the summation is 3001.1 minus mu, which is negative 0.4 squared. And when we go through the process, we end up with 54.78. What does it mean? And that's really important, the interpretation. Pay attention to mu. Mu is negative, and it is supposed to be negative for the players and positive for the house. So that would be the net gain on the average per player for the house, positive, and for us, negative. So the interpretation is, on average, a player, all players, everybody loses an average of 40 cents or $0.4 per ticket with a standard deviation of 54.78. It's important to understand, on the average, everybody loses. On the average, everybody loses, including all the winners. So I want you to see the concept. And that's how many things are calculated. Even car insurance or health insurance is calculated using this concept of expected. We could use a different method, and I'm going to mention it in this case, to calculate this, but it is not as detailed as this one for the expected value and the variance and standard deviation. But at the very least, the cost is $2. But what is the amount of prize? The amount of prize is 1,000 divided by 10,000 times 5 for $5 winners. That's why you multiply it by 5. For $10 winners, it's 100 divided by 10,000 times 10. $1,000 winners, 5 over 10,000, and there's only one that wins 5,000, wins big. And all of them, if you add them up in this fashion, if you will, minus 2 gives you the same mu, or the expected value, negative 0.4. So this would be another approach, but the previous one is more detailed.
$5 to place on a bet in a casino. Let's consider the following two bets. Roulette. Bet on the number 7 in roulette. The probability of losing is 38 over 30, 37 over 38. The probability of winning is 1 over 38. The net gain is $175. B, craps. Bet on the pass line in the dice game of craps. Probability of losing is 251 over 495. The probability of winning is 244 over 495. Net gain is $5. Which bet is better?
Which one has better expectation? E of x or mu? That's the idea behind the question. We are going to look at the two events, and we're going to put in the information that we have. So all we have to do, what is x, what is p of x? For the first one, losing is at -5. That means the $5 that we put in. However amount that we play, $10, whatever. And the probability is the next column, 37 over 38. You win 175, 1 out of 38. Now, for the next game, so for event A, if you will, roulette, and now event B, we do the same losing, -5, and has a different probability. Winning is also different, not just the probability. The amount of winning for roulette was 175, but for this one is only $5, but it does have a different probability. Now we are going to calculate mu, or the summation of x, p of x. It means we have to multiply the two columns and add them up. The columns are x and p of x. Let's calculate their product and add them up. Okay, so we are interested in calculating mu equals summation of x, p of x. So with that being the case, when we multiply -5 by 37 over 38, and then we multiply 175 by 1 over 38, and then we add them up, we get -0.4 0.26. We do the same thing for craps, negative 5 times 251 over 495, plus 5 times 244 times 495. And they add up to negative 0.07. As you can see, both of them are negative. What does it mean? That means the roulette has a total of negative 0.26 for the players as the expected value, and it has a positive 0.26 value for the house. Craps has a mu, or the expected value, of negative 0.07 for the players and positive 0.07. And so here's the interpretation. When we bet $5, the expected value for the roulette is negative 26 cents. So every player on the average will lose 26 cents. And for craps, 7 cents. What does it mean? The craps game is better in a long run. And I can't emphasize this enough. Obviously, some people may go for higher risk, but that's how statistics work, the expected value. So for a long run, even though the roulette game provides an opportunity, a larger payoff when playing the game once. So in a long run, those are the gains. Negative 26 cents for roulette, negative 7 cents for craps. By the way, the numbers that you see here, the probability that you see here, just for the sake of argument, if it changes for any reason, according to the type of roulette or craps is being played by a specific place, so be it. But this is the general concept as to how we evaluate things using statistics.
In a casino, the house wins on one of its games with a probability 50.6%. All bets are 1-to-1. Therefore, if you win, you gain the amount you bet. If you lose the amount you bet. If you play 200 games betting $1 each time, how much should you expect to win or lose?
We are going to go through the process and do the calculation for the event. And all we have to do, calculate mu by having two columns, x and p of x. That's what we are going to do. So here's the simple setup for the table. X, so the probability of the house wins, understand that means losing for the player. So the house winning, that means 50.6% there's a chance that we lose as players. If we play $1, so that means we lose that. Now, if this is the case, what is the probability of winning and the amount of winning? Well, we are playing with $1, let's say, or however amount. So that would be X, but what is the probability of winning? 1 minus 50.6%. That's how we arrive at that number, or 0.506. So the answer is 49.4% or 0.494. I put one of them as a percent on purpose because it's given as such, on purpose. Needless to say, really it makes no difference, and it's better to write both of them as percentage or decimals, but I did it on purpose. I want to keep it just the way it was given, and then 1 minus that. That's how we arrive at 0.494, because the sum of probabilities is always 1. All right, so we calculate mu, summation of x p of x. We multiply the first column by the second column. So negative 1 times 0.506 and positive 1 times 0.494, and we add them up. And this is the amount, the expected value, the average amount, the mean for winning in the case of one game. And that's for one game. But if we did 200 games, we multiplied by 200. So the expected value for 200 games would be the loss of 200 times the amount we found, which was negative 0.012. So again, for one game, the expected value would be negative 0.012. And for 200 games would be the same thing times 200, which becomes negative $2.4. This is the dollar amount.